In Buddhism, there is an old saying, form is emptiness. Here, form refers to objects, the tangible matter, while emptiness signifies nothingness. The surface meaning of this phrase is that the seemingly solid objects are actually empty. You might think this is a Zen expression, conveying a philosophical idea, but modern physics, the deeper it delves, increasingly suggests that the reality of the world may indeed be like this. Many physicists today will tell you that most matter is empty, including stones, trees, and even humans. Many people are familiar with the fact that atoms, which make up these things, have most of their mass concentrated in the tiny atomic nucleus, and the space between the nucleus and the electrons is mostly empty. In an atom, the atomic nucleus contains more than 99% of its mass, but the space it occupies within the atom is comparable to an ant inside a football field. Don't rush to ask why such tiny matter has such massive mass. If we go deeper and ask what mass really is, this question leads to even more astonishing answers. We live on Earth, and everyone can feel the presence of mass. For ordinary people, mass is directly related to the force of Earth's gravity, and its manifestation is the weight of an object. If we lack exercise or often stay up late, we gain weight, or more strictly speaking, our mass increases. When your own mass increases as an object, you will surely analyze what parts of your body have added weight. Generally, the added part is fat, and thinking carefully, the amount of fat you gain is the amount of mass you gain. This is quite intuitive, right? But here we must emphasize once again, the more intuitive something is, the more likely it is to violate the most basic laws of physics. Let's re-examine the issue. If an object has mass, is its mass simply the sum of its parts? If you cut a watermelon into two halves, the total mass of the watermelon should equal the sum of the masses of the two halves. If you cut it into 4 pieces, the total mass should be the sum of the 4 pieces, and so on. If you cut it into n pieces, you can sum up the masses of the n pieces to calculate the total mass. This is correct in most cases, but if you cut a piece of watermelon small enough, say to a size where n exceeds 10 to the 23rd power, things change. Let me tell you why. The total mass of that watermelon includes not only the mass of its parts but also the energy that holds the parts together. You may have never heard of this idea. Let's first talk about the strict definition of mass in physics. Mass is a property that resists changes in an object's velocity. If you push something, it accelerates, and if you push another object with the same force and it accelerates more slowly, we say the second object has more mass. Imagine, even on a smooth ice surface, pushing an empty cart requires less effort than pushing a cart with a person in it. We say the cart with a person has more mass. However, mass does not fundamentally make something harder to push. Our understanding should be the opposite. If something is harder to push, we define its mass as larger. We define this resistance to acceleration as inertial mass. Now, let's return to the watermelon cutting example. When you cut the watermelon very, very small, to the atomic level, the binding energy that holds the atoms together can be broken. The total mass of the watermelon, when cut into tiny pieces, will decrease. In fact, when you cut a watermelon in half, its mass decreases, but the decrease is so minuscule that you don't notice it. However, if you cut a watermelon down to the atomic level, measure the mass of each atom, and sum those masses, comparing this with the original mass of the watermelon, you will find that the mass has indeed decreased. This is not just a calculation, it's a phenomenon observed in the laboratory. Of course, in this example, the loss of mass is relatively small because the overall mass of a watermelon is not very large. In this experiment, if we cut the watermelon into atoms, then into protons, neutrons, and electrons, how much mass would be lost? Roughly 0.001%. But if we started with a much smaller object, the situation would be very different. For example, if you split a proton into quarks, as we discussed in the previous episode. In the process we've discussed, when we talk about up quarks and down quarks, you will see a huge difference in mass. The mass difference is so enormous that you will realize that most of the mass of protons and neutrons comes from the binding energy that holds the quarks together. After cutting, what is the ratio of the mass of the quarks compared to the original proton's mass? It's about 1%, and the remaining 99% comes from the energy that gathers the quarks together. In other words, the energy stored in the bonds between particles is much larger than the total mass of an object's parts. It's 2 orders of magnitude larger, which is completely counterintuitive. Imagine you pick up 3 ping pong balls and measure their individual masses. You can directly calculate the total mass of the 3 ping pong balls. This is simple, right? But if you place these 3 ping pong balls into a furnace with a huge amount of energy and compress them into a new, smaller ball, you'll suddenly find that the new ball has a mass much greater than the combined mass of the 3 original ping pong balls. The reason is that the mass of the new ball comes not only from the mass of the original ping pong balls but also from the energy that binds them together. Think carefully. If you weigh 150 pounds, the actual mass in your body is only about 1.5 pounds. The rest of your weight comes from the energy that holds the particles together. Doesn't that seem extraordinary? So, do scientists know why most of our mass comes from this energy? Honestly, they don't know. Scientists truly don't understand why this energy influences how an object reacts to force. When you push an object, you only directly feel its material weight, not the energy inside it. This is the greatest mystery of mass. Although we can measure the mass of an object, we really don't know what inertia is, nor do we understand why it has such a peculiar relationship with mass and energy. It's like knowing that the speed of light is the universe's limit, but not knowing why such a limit exists, or who set it. Now, by this point, your brain might have been struck by a powerful blow, but let's make it even more intense. Earlier, we mentioned that protons and neutrons can be broken down into up and down quarks, but you should know that quarks aren't actual things. In fact, there's no such thing as things at this level. When we reach quarks, physical objects as we understand them no longer exist in the realm of physics. In our current theories, quarks are indivisible points in space. Theoretically, they occupy an infinitesimally small position in 3-dimensional space, with a volume of 0, meaning they have no size. What does having no size mean? Every one of us is made up of particles, but each particle occupies 0 space. This doesn't mean that most of an object is empty, it means that the entire object is empty. Now, let's think again. When we say there are no things in physics, what does that definition mean? Think about it. An object has mass and volume, and mass divided by volume gives its density, right? But now, if you ask about the density of an electron, this question cannot be answered. Why? An electron has mass, but its volume is 0. We know from elementary school that dividing by 0 is impossible, so the density of an electron is undefined. Let's take a look at quarks again. In the previous episode, we showed you a table of quarks. In the first row, the first and third columns contain the up quark and top quark. These 2 quarks carry the same charge, have the same characteristics, and experience the same fundamental forces. The only physical quantity that differs between them is mass. How much is the mass difference? The top quark is 75,000 times heavier than the up quark. If you understand this in terms of conventional matter, you would think that the top quark must have a higher density. But in physics, their occupied space is 0. So, here's the paradox. Why does one quark have so much mass, while the other doesn't contain more material? This problem seems so perplexing because quarks aren't like what we imagine. In fact, we don't even know what real particles actually look like. To know what an object is, you must be able to observe it. But when we talk about a particle, we don't even know what real particles actually look like. To understand what an object looks like, you must see it, right? But when we break a particle down into extremely small pieces, its diameter is many, many, many times smaller than the wavelength of light. We simply cannot see it by emitting light. Now, if you insist on asking, what does a basic particle look like? This question is one that not only physicists can't answer, but it also doesn't even make sense. In quantum mechanics, these tiny particles are small fluctuations in a strange field that permeates the entire universe. This means that the classical Ball model cannot explain the laws they follow. For example, the position of a particle follows probability. There's a 99% chance that you can find this particle in your room, but there's also a very low probability, like 0.0000001%, that you could find it at the farthest end of the universe, but it has to be at the same time. Another example, a tiny particle has a certain probability of passing through any object, like the walls and doors of your house, and appearing outside without needing any external force. The behavior of tiny particles is incredibly strange. In modern physics research, the particle model has already failed. For example, a photon has no mass, which is why it can travel at the speed of light. But a photon has neither volume nor mass, so how could it be considered an object? If you insist that an object must have matter, meaning it must have mass, you will inevitably conclude that a massless particle doesn't exist. But let's open our minds a little more. What if mass isn't an inherent property of an object, but rather a label we attach to it? To emphasize again, this shift in perspective is very important. If mass is not an intrinsic property of an object, but instead a label we assign to it, does it make sense to think about it this way? You might find it difficult to imagine mass in this way, but actually, we've already been doing this in other fields. For example, when we discuss the charge a particle carries, we're doing just that. We know that electrons have a negative charge, and protons have a positive charge. So what exactly is this charge? Where exactly is it located in the electron and proton? Is the charge carried on the surface of the electron or inside it? What is it that gives the electron its charge? Since the electron's volume is zero, does it have enough space to hold this charge? In fact, no one asks these questions because charge is not a real thing that the electron carries. It's simply a phenomenon we observe when studying electrons, and we attach a mathematical label to this phenomenon. It's similar to when you see that a banana is yellow, you don't say that the banana carries some yellow object. Instead, we observe the combined color and simply label it. If you think about mass the same way, it makes sense. If charge means a particle can be influenced by an electric field, then mass means a particle can be influenced by a gravitational field. The charge of an object determines how strong the force it experiences will be in the same electromagnetic field. Similarly, the mass of a particle gives it its inertia, meaning its ability to resist motion in a gravitational field. As we mentioned earlier, the top quark is much more massive than the up quark. This doesn't mean the top quark contains more material with mass, but rather that the top quark is more difficult to move within the entire gravitational field. Its inertia is greater. This is just a label. Now, we have to talk about something new. And its name is really cool: the Higgs boson. And with that, we've reached the end of part 1. But we're just scratching the surface of this fascinating topic. In the next video, we'll dive deeper into the Higgs boson and explore how it fits into the bigger picture of particle physics. Stay tuned to find out how this mysterious particle impacts our understanding of mass and the universe itself. This is Cosmos Unlocked. See you next time.